Okay, welcome back. You guys coming in late, just come on down and get a seat somewhere. By the way, if I have the final roster downloaded this morning from the registrar's portal. So if you're not in the class, and if you're hoping to get a spot in the lab or something like that, it ain't gonna happen. It supposedly happened Thursday night at midnight. And so if you're going to get in, that's it. And so if you're not on the roster now, uh, you probably are not going to be able to get into web courses. And for sure, for certain, you won't get a grade at the end of the semester because I don't have any way to give a grade, even if I wanted to. So um, last time we finished talking about uh, this basic calculation average speed, the change in the position, delta S, and students, I use the symbol S to mark a generic axis. So X and Y, the X-axis is, usually envisioned as horizontal. The Y-axis is usually vertical, as in looking down on a piece of graph paper. And the Z-axis is perpendicular to both of them and coming out in the third direction. But if you have some other axis, like what we were doing on Friday, kind of on a slant, then you can use just the generic symbol S. And the average speed, delta S over delta T, we did that calculation. And here is, we're going to go over this calculation again just for safety. Here's the specs. You had a clicker question for this. And many of you calculated the speed, 5 meters per second. I asked you to round off to the nearest whole number. So you just had to type in a number and hit the send key, which many of you did properly. All right, and then I gave you, before dismissing, I gave you a challenge problem. Could you figure out the tilt angle of the velocity vector? And of course, the answer, some of you said, yeah, you could use a little bit of Chief SOHCAHTOA. Who ever heard of good Chief SOHCAHTOA for the trig? Sine, it's spelled SOHCAHTOA. Sine opposite over hypotenuse, CAH. Cosine adjacent over hypotenuse. Tangent opposite over adjacent. I did not learn that. You know what? I didn't learn that in high school or college. I learned it when I became a teacher. And some of my students, oh, Dr. B, Chief SOHCAHTOA. Anyways, we're going to do that today. And what we're going to do is a talking PDF on the document cam. And I'm going to try to do this a couple times a week. We'll actually do 2 talking PDFs today of that calculation. So I'll be recording. You'll see how it works when you download the PDF from web courses. I'm going to pause the, just so you know, I'm going to try to do a lot of these talking PDFs simply because it's something that you can use easily. It works nicely, and you can hear my narration, and that's definitely going to help. Plus my handwriting and my sketching. And I hope when you use that, it will help you form your problem-solving thought patterns. And here's another thing: when you're listening to mine, don't think that's the only way to get to Mississippi. I mean, there's a lot of roads. And pick another 4 faculty, another 4 grad students, and another 4 you guys. And with the same problem, you'd have 12 different explanations, but getting to the same answer, hopefully. So, all right, let's keep going. Now, I wanted to get to this last time. We did get to it, and it's introducing us to something important, and that is the distance formula in its most basic form. Like if you have cruise control, on your car, if you have a car that's, got cruise control, you put it on and you're heading for Miami, a couple hundred miles on the turnpike. And since you're nice young men and young ladies, I know you never go over the speed limit, so you just get it up to 65 or 70 or whatever the speed limit is, hit the cruise control, and then you're cruising along at a set speed. So if you want to calculate the amount of distance you go, you just multiply by the amount of time. Okay? So it's speed time, and it's based on this formula. So the delta x down the highway, just your cruise control speed, times delta t. The other way that you could do it is to figure out, and I don't have it on here, but to figure out the drive time. You take the distance to Miami and divide by your cruise control speed. So that would be delta x divided by v. And that'll get you the amount of hours. I mean, if you input your speed in miles per hour, then your drive time will be in hours, 1.3 hours, or, well, that's a little bit short for Miami. But that's like going up to Gainesville or something like that on a turnpike. Now, there's another way of visualizing the motion of an object, and this is from chapter 2.3. We're going to be mostly in chapter 2.3 today, and that is using a graph. And I cannot overemphasize and we're going to do a talking PDF of graphs, velocity graphs. The reason for it is because there's a trouble with averages. If all you know is the average speed, you don't know jack about any specific moment along the road to Miami. So for instance, if you tell me, okay, I drove 237 miles to Miami, is that about how far it is from here? 230, yeah, so 237 miles to Miami, and it took me 3.8 hours. No, let me say, it took 4.6 hours to go 237 miles. You can get an average speed, but it doesn't tell you, how much time you might have slowed down to stop at the rest area and get some snacks, some Cheetos or something, or some gas, or a combination, And so in chapter 3, they have this nice sentence: the average velocity of an object does not tell us anything about what happens to it between the starting point and the ending point, however. Okay, there's information missing. So, and a good example of how the average speed is deceptive is the story of the tortoise and the hare. The hare has a lower average speed, so he lost the race. But it doesn't tell you that what he was moving, he was really moving faster than the tortoise. And it also doesn't tell you that the hare took some naps, for Cheetos and stuff. Had a little Dunkin' Donuts break or whatever, and so the average speed is good, it's helpful, it's nice, but it doesn't tell you everything. But what does tell you everything, almost, is a velocity graph. So write down figure 4, chapter 2.3, here it is. And we're going to talk about this particular graph in detail. It's figure 4, chapter 2.3. And hey, you guys, I'll try to use graphs from the book, our free online book. And I've been using pull quotes, and I'll try to identify. I don't think they have page numbers in the book. So the most I can do is 2.3, and then it's not hard to find. So. Is there?
Yeah, if you want the page number for the actual book, or the page number for what is.
Yeah, well, like for this diagram, for instance. I didn't see the page. I'll have to look at it again. Anyways, I'll try to identify the diagrams and stuff that I use. A lot of the diagrams are my own manufactured, but this one I like. Okay, so this is it, and we're going to look at it. We're going to blow it up here in a second. But first, the top one is position versus time. So this is where you are on the x-axis, and over here, where the white arrow is up here at the top, um, right here, you can see that the x coordinate is, I don't know, is that a 3 up there? It's getting up to about 3 meters to the right. All right. Now these are abstract graphs. You can't say that, well, if I'm in a drone overhead, I can look down and at least see the path that looks like these diagrams. You can't do that. It's not like graph paper and x, y coordinates. This is x and t. So you can't, it's a little bit abstract, but it's still useful. So you go in about, what is that, 0.2 seconds? Hours. Okay. I should have spec'd that out a little bit better. So 0.2 hours, you get 3, what is it, kilometers down the line. Okay. And then you start back, and eventually you get to 0 over here. So over here, you're on your way back. Now, the significant things about this are the slope, okay, as well as the graph itself. Okay, so write down the slope in a position versus time graph. If you think about it, and when I say slope, I mean, just good old 10th grade algebra, geometry class, rise over the run. The rise is, yeah, that's kilometers. The rise is the change in the position. So that's delta x. And the run is the change in the time, the elapsed time. Okay, so rise over run is a speed. So the slope is actually not just a speed, but a velocity. Because this upward rising to the right, that's a positive slope. This guy's gaining bigger values of the x-axis with time. Now over here, on this part of the graph where the arrow is now, that's negative slope. He's dipping to the right. And that means physically he's going backwards now. He's going, instead of heading, let me ask you, I don't know the answer to this. When you head to Miami, the mile markers get smaller, right? When you head south? Okay. So this guy started in Miami, headed north towards Kissimmee, turned around and went back to Miami. So over here, he's going to smaller and smaller mile markers. Okay, smaller and smaller values of the x coordinate along the turnpike. All right? And so his velocity is negative, and on the turnpike that would mean back towards Miami, south. Okay? And set on graph paper, south is, on maps, south is downward, north is upward. All right. So the slope of this graph is interpreted as a velocity. Remember that. Question. Here in front? No? All right. Hey, what were you guys doing in lab last week? You were doing what? I didn't hear. I heard somebody say cheeseburgers. What? Martin, what were you doing in lab?
We worked on a set of worksheets and like basic terms for physics, and also like introductory test of testing our knowledge.
Yeah, I know which ones you're taking. Yeah, okay. And a worksheet. All right, what are you supposed to be doing this week? So time and delta x and delta t and all that stuff. All right, so that's good. All right. Now, this middle graph here, this one's actually the most important one. This is a velocity graph, velocity versus time. And this is for the same motion. The slope here in the upper graph position is positive, and that means this green line segment here, until it turns around anyways, is up in the positive upper half of the graph. So the upper half of this velocity graph is rightward motion. All right. And so the left, the bottom half, like down here it says -10, and I guess that's kilometers per hour. Yeah, kilometers per hour. So down here you have a negative green bar below the time axis. And remember, this is time on the horizontal axis here. So this is another abstract graph. So this is down here. It's negatory. And so that signifies that you're heading back to Miami. All right. And then this is kind of a connector for the graph here. All right. So you've got the first half of your motion, an upward triangle here, a flat line segment here, because it means that you have a constant speed. And on the position graph, you have a constant slope. Rise over run, it's a nice straight line. It's not curving or anything like that. Now, we're going to be talking about a position graph where we do have some curve to it. But this one's nice and flat. All right? And this one, this velocity graph, here's the negative one down here. This is really important for us. And I'm going to ignore the one below that because I don't like it at all. So, matter of fact, I might put a nasty note in there because I can put nasty notes into the customizable UCF version. Anyways, the first two are the ones that I like. And so this is the velocity graph, kilometers per hour. And it's velocity, it's not speed. It actually tells you the direction. It encodes the direction. And if you think about it, it tells you the velocity at every instant of time. So this is not, you can figure out an average speed from this. That's nice. For any time interval you want. But this one, it encodes extra information in the graph, and that is significant for us. Question?
Yeah, so for instance, like -10, that means like you're going 10 kilometers per hour like south.
Right. Yeah. So this one looks like it's I don't know, about -13 or so. So you're going -13 kilometers per hour to the south, back towards Miami.
That was at the 2.5 or 0.25 hours.
Yeah, after about 0.25 hours, whoops, I forgot something at home. I got to head back to Miami. Okay. And then here you are, just tooling along, heading for UCF, and then, oops, I forgot something. Got to turn around and go back. And you've only gone about 10 kilometers, so it's not that bad. So not even 10 kilometers. And matter of fact, how far you go is exactly the point here in this problem. Another question. Now, we'll keep going. The velocity graph. You may think to yourself, Dr. B, why are you so obsessed with the velocity graph? Well, I'm obsessed with it because I saw this motion picture, Hidden Figures. Raise your hand if you saw that. Oh my goodness. One of the totally awesomest movies of all time. And of course, those are the Hollywood actors. Here's the real thing. There's Katherine Johnson in the middle. She's the hero of the movie. And then that's the real Mary Jackson. And this is the real Dorothy Vaughan when she was young. And Katherine Johnson, the whole thing with Katherine Johnson, it's really true. John Glenn did ask her to double check the figures because they wanted to know where that spacecraft was going to deorbit and where it was going to land. And that's what Katherine Johnson knew how to do because she knew how to interpret velocity graphs. She was an expert at doing the stuff that you now know the kindergarten version, Velocity Graphs 101. And she was, Professor Katherine Johnson, and Mary Jackson and Dorothy Vaughan the same. They all knew how to make these calculations. And in fact, here's Katherine Johnson. Oh my goodness, she's 100 and something years old now. And she got the Medal of Freedom a couple years ago at the White House. And this is the key to Katherine Johnson's analysis. The smaller the time intervals considered, the more detailed the information. When you have got, think about it, you guys are in lab right now, and you've got those hokey carts with metal wheels, right? And they're made of wood, right? And you put weights on them, right? And you roll them down the table, and you time them, and all this kind of stuff, right? Okay, so that's very, very easy to handle. But think about a rocket. Think about a spacecraft. You launch a rocket. Just think about it. It's got tons and tons of rocket fuel, right? So it's really heavy. But then you light it off. And when you light it off, ignition, you go skyward. And you start losing tons of mass at the rear, at the rocket engine. And that's what makes, all that rocket exhaust goes downward, the rocket goes upward. And so that is an extremely difficult problem because the mass is changing, unlike the things that you were doing or going to be doing in lab this week. If you have a changing system and it's accelerating, very difficult. But distance polygons, like we're going to be studying today, make it all possible. And what they have to do is, like the distance graph, the velocity graph that we were just looking at, that was in increments of 0.2 hours, 0.1, 0.2, 0.3, and so forth. But for Katherine Johnson and NASA, you're talking milliseconds that they have to recalculate speed, velocity, and position. Because if they don't, your spacecraft could be lost. And we have lost space. We've never lost any men. We've never lost, not from miscalculation. We've lost, from catastrophic failures, but never because our positions were incorrect. We have lost, we put a Martian spacecraft, we launched something to Mars a number of years ago, and it crash landed somewhere on Mars. Because you know why? Because somebody made calculations in English, feet, miles per second, and the other people in the project were using meters and kilometers per second, and so they got it all screwed up. So they don't know if it overshot or undershot, but it was lost. It's happened a few times. All right, so now I want you to write down, we're going to do another example on the document cam. And let's just go ahead and write down the specs. Okay, we're going to start out at 0.0 meters per second at time t equals 0.00 seconds. In other words, we're going to start out at rest. All right. So on our velocity graph, we're going to start out at the origin. All right. And then we're going to steadily acquire, here we go, 2.0 meters per second of rightward speed. So we're going to be in the upper half of the graph. For every second of travel until t equals 4.00 seconds. All right. So that, my wonderful students, is called acceleration. All right. Then we're going to coast for another 6 seconds at whatever the speed is, and we'll figure it out on the document cam. And we're going to coast for another 6 seconds. So that means now you're in the upper half of the velocity graph, and now you're coasting at that speed, and so you're not dipping upward. Now you're flattening off on your velocity graph. So our velocity graph is going to go up at an angle, rise over run, and then it's going to flatten out for 6 seconds, all the way out to 10.0 seconds. And so then what we're going to do is ask ourselves questions like this. How much distance have you covered in 10 seconds? What's the average speed of the first 4 seconds? What's the average speed for the first 10 seconds? You know, so you can figure out an average speed for any time interval you want. And, you know, a speedometer in your car is figuring out average speed for very, very small elapsed times. You know, I don't even know what it is, but it's got to be like fractions of a second. Another one, what's the instantaneous speed at 3.00 seconds? I'm going to introduce that topic, instantaneous speed, etc. All right, so let's go to the document cam and work this out. Now, let me pause the YouTube again. Get my cursor back over here. Come on, baby. So we did a good job with this example. I'll pass over these questions. Definitely look up this example from chapter 2.4, the subway train. We'll talk about it on Wednesday. We'll go through all these slides here. I want to get to this homework. Come on, baby. See, there's the curved, oops. All right. So here are the study problems that I like. All right. And it's already listed in the, you don't have to take a photograph of it. It's on the homework list in web courses. All right. So it's a bunch of them from 2.3 and one from 2.4. But don't dismiss yourself quite yet. You can look up the answer for each one. So work on it with a friend. Make sure you know how to do it. Also, you're going to have written homework that's going to be due Friday, and I'm going to publish it as a PDF in web courses Wednesday, if not sooner. And what it's going to look like is this. There's a page right now at the very top, and this is from summer, so it's a little different topic. It's about molecules and stuff. At the very top, there's the problem. You know, the date and all that stuff. And yours will look like something like this. And then down at the bottom is going to be a grading area. And you don't write in that. I'll be writing in that. And the TA will be writing in that. That's where you'll see your score. All right? So try those homework problems out that I like, and I'll see you on Wednesday. Good class today.